Marco telling us about renormalization group flow in ADS and the Bootstrap program.
Okay, thank you very much. Okay, I'll start by thanking the organizers for the opportunity to speak and for bringing us all back to Sao Paulo the second time around. And then, okay, yes, we'll be talking about quantum field theory in ADS and try to set up a bootstrap problem which allows us to follow, hopefully, renormalization group flows all the way to flat space. So this talk is about setting up the problem, and I won't be showing any plot because we didn't do the numerics since we knew that at the Bootstrap conference we wouldn't be allowed to show the plots. So next year, hopefully, they will cut us some slack, and then we'll have plots to show you. Okay, so the overview is written here, and I would directly get to it. We'll see step by step where we're going. So the first item is some introduction. We want to talk about ante-de Sitter space as a lab. So this all starts with a question. The question is rather counterintuitive. It's, can we study massive QFTs via the conformal bootstrap? And okay, this question is counterintuitive, and this speaks about the creativity of the people that asked it first. And the answer is yes, but it's not easy. And this was put forward first in one of the two starting papers of the S-matrix bootstrap story by Miguel Paulo, Joao, John, Balt, and Pedro. This is the first of the two papers, the better one, because it's the one that wasn't scooped. Right, so that's, and okay, so the idea is in this picture where we have ADS, which gives us quantum field theory in a box, and at finite radius, finite r, boundary correlators are constrained by the isometries to be to obey the conformal isometries of the boundary, so they're conformal 4-point functions that generate these scattering events in the bulk. And when we take R to infinity, so here we have conformal 4-point functions. And as R goes to infinity, we get flat space physics. So, okay, this method, physics, is computationally expensive because we need to take R going to infinity, but it has some advantages. First of all, so advantages. The axioms are well understood. And this has practical consequences in the sense that this includes multiple correlators, so scattering of particles with different masses in the flat space limit, or higher point in principle. So this comparatively in flat space is much harder because the analytic structure is not understood, and here maybe one has a shot at just making it come out of the computation. And then another advantage is that this is not a deep advantage; it's sort of practical or maybe even just historical advantage. That the dual formulation is ready to be used. So the dual formulation of the bootstrap is, say, the most natural one for the questions one would like to ask. This is more and more less relevant because there's dual formulation for the S-matrix in flat space, which are being developed, but it's fair to say that for some observables, it's more natural to ask in this language, for instance, observables which are coupling which are not dispersive. So this is slightly easier. The disadvantage, as I already said, is computationally expensive, and there are some other issues that one, well, not really comparatively to the S-matrix Bootstrap, but some other issues in this method that I will get to in a second. So the original setup was well suited to ask sort of questions about the space. So questions that you could ask are about the space of quantum field theories. Typical question is, what is the largest cubic coupling given a hierarchy of masses? So this includes all quantum field theories, and you're looking for some maximum. So eventually, we would like to get to some more discriminate questions. So what about some specific hierarchy of IR masses, given what the UV conformal field theory is? Let's follow the flow. This is a question we might want to ask in the future, and for this we need a handle on the UV. So this work is one of the aims of this work was to try and provide some handle on the UV. In flat space, this program, this specific problem of injecting the UV was started by Dennis, Joao, and Simon Kuhn in 2019. And today we try to ask the same question in ADS. This also, we essentially upgrade the program to anti-de Sitter space. So let's therefore have a look at how an RG flow looks like in ADS. RG flow. So we have our nice arrow going down in energy, some UV, some mass, and the ADS radius. So we're going to think in terms of some CFT deformed by a relevant operator, which I call V of X. This is integrating in ADS. So delta V is less than D plus 1. I will always use the sort of ADS CFT kind of notation. So we're in ADS plus 1, the boundary is D-dimensional. And okay, so first of all, reminder, so a conformal field theory in ADS is equivalent to a conformal field theory in a flat space with a boundary, because ADS is conformally flat and it has a boundary. So we start by a BCFT, and then B stands for boundary CFT, and then we perturb. So this scale M, so this is sort of a simple setup where there is only one scale. So this M is related by order 1 numbers to lambda. And then we're using R, we'll be using R as our sliding scale to focus on one part of the RG flow. Here I denoted as a specific hierarchy, so when 1 over R is smaller than M, so in particular, in this case, if we take the limit, the RG flow happens directly in flat space. Curvature corrections are invisible in the limit. So in this limit, we get an RG flow in flat space. While in the opposite limit, so if we bring this scale up towards the UV, essentially the RG flow doesn't start, right? In the limit, we're immediately saturated by curvature correction, so we see exactly the BCFT. So we go back to the UV BCFT. And this translates in practice into plots, which I can draw there. For instance, if we look at the spectrum of scaling dimensions in global time, which are the energies in global time, which are scaling dimensions of the boundary operators as a function of this of the radius, we would see some plot of this kind. I'm assuming that the theory in flat space is massive, otherwise there's some obvious modifications, but okay. And okay, there might be some other trajectory with another lines, etc. But the idea is that here we have the BCFT spectrum we start from, spectrum of boundary operator in the CFT, and then when the radius becomes large, so we go into this regime, we're getting some linear trajectory, some tangent, which is given by this formula in terms of the flat space masses or energies. So this is visible, well, on the nose in free theories, like if you draw the spectrum of free boson, and it's also visible to some extent, so we cannot quite get to the flat space limit if you pick specific truncation scheme, for instance, Hamiltonian truncation, you can study interacting theories and sort of get out a spectrum which looks like that, which is something that we did a couple of years ago with Matthijs and Cameron and Joao. So, okay, so now we'll try to follow along. So you could try just to follow along some of these curves. So the idea is try to get some moving islands, for instance, in which you go from the UV to the IR, or maybe getting some correlator to be extremal, so saturate from the UV to the IR as a function of the ADS radius. And this was explored in a nice paper which is already on the archive and the paper which is upcoming by Antonio, Miguel Costa, Joao, Aditya with two A's, and Balt, and by Antonio, Edo, and Balt, who talked about it. Balt talked about their upcoming work last week in the afternoon. So these are very instructive results, and but they also emphasize the two extra issues which are a bit the focus today, which all have to do with the size of the quantum field theories we want to study. So one is that the space of boundary correlators is hard to disentangle from non-local theories, which don't have, so they're non-local, they're non-local in the boundaries, but don't have ADS bulk. This is something that is not immediate to input from the point of view of just a 4-point function. And then if we look around the UV fixed point, right? In this we try to follow immediately in the neighborhood what is parameterizing the possibilities, so the correlators that would obey the bound. While you might expect there are the relevant deformations, so the things we want to study, but also all the irrelevant deformations. If there are quantum field theories that flow to that UV fixed point, they pass close. Well, there's no immediate way to exclude them. So we also have irrelevant deformation. Okay, so today I would like to talk about an attempt to both input in this system bulk locality and get rid, if possible, of irrelevant deformations. And in particular about the first topic, I need to say immediately that there was a paper by Miguel and Nat that addresses very, very similar questions from a slightly different perspective. The results were very useful for us, so I will mention this paper more in detail when the time comes. And Nat is going to give a talk on it tomorrow afternoon, so this is going to be a natural, yeah, you should definitely go to that talk if you're here. Okay, so the issue is that they enlarge the space of possible quantum field theories, and they sort of, it's hard then to follow a relevant deformation instead. So the practical consequence is that in this paper you will always find, so they did some perturbative analysis, for instance, around the UV fixed point, and you will see that with respect to the boundary of the allowed region, theories that you want to study, say Sine Gordon or 5 to the 4th, etc., they tend to go inside. And okay, and they also see that sometimes tangent directions or many of the directions in these plots are labeled by irrelevant deformations instead. And okay, you would like ideally to take, so one way to sort of get rid of these in the islands, for instance, like to try to input gaps which are appropriate, but also those are sometimes not sufficient. So this is the issue, yeah. Okay, so we can move on to part 2 if there's no questions. Are there other questions? Otherwise, I'll move on to part 2. And this I can erase, I think, because I don't want yet to erase that. Okay, so we would like to describe this Bootstrap problem. That sees the bulk. So what we'll do will be to add to the 4-point function two other consequences of two other correlation functions, which I directly drew here, so I'm going to refer to this board now. So here we have the usual 4-point function where we have OP coefficient squared, the usual crossing equation that follows from that. And we'll consider two extra correlator. One is the correlator of two bulk stress tensor operators, and one is the three-point function of one bulk stress tensor operator with two boundary operators. So what's the reason for that? Well, the most direct way of inputting the bulk is, of course, to consider bulk operators. This excludes all the theories that don't have a bulk, at least hopefully. And then from this one, in the same spirit as the homologic of C theorem, you can get some rule in 2 dimensions. This will be valid in 2D, so ADS2, that gives you the central charge. So this will input in the Bootstrap the value of the UV central charge. So this should be the thing that gets rid of the irrelevant deformations, hopefully. And then we need this because we need these two problems to talk to each other. So we need some piece of data which includes both. So this BT delta, I will describe in a moment what they are, but they're extra CFT data. And we have another sum rule, which comes from that correlation function, in which the product appears. So altogether, we have a positive semi-definite program that we could hopefully, well, we can definitely plug into STPB, and hopefully will give some more precise data. Yeah. Okay. So what are the BT delta? Just very quickly. So BT delta is just what appears in the boundary OP decomposition of a bulk operator, in this case, the stress tensor. So when we bring it to the boundary, there will be some decomposition. Schematically, we'll have, well, I'm getting rid of all the kinematics, but the gist is that there will be boundary operators and some OP coefficients, which are these B's. Okay, so this kernel I wrote explicitly. This is simple enough. This one I didn't write, essentially because it's ugly. But what's, I will comment more at length about this kernel, but and how we get it, but what's important here to notice immediately is that there is a one parameter family of some rules. And this is the part where, which is really strongly related to the work of Miguel and Nat. So we'll get to that in a moment, but yes, so there is one kernel that depends on one parameter, and the other one is just a sum rule with no free parameters. Yes?
For the bulk correlator, is it really crucial that it would be the stress tensor, or if we knew that the bulk theory has some local scalar field, for example, we could also cook something up?
You could cook something out. What is not obvious is what's going to lie on the right-hand side here. Mm-hmm. So we wanted something that gives some bulk data. But for instance, if you want to do it in higher D, maybe we'll see that you don't get really the central charge, so it may be useful to use something else. But you do want to have something that specifies the theory in the UV. Another example that would clearly work is if you put a current here. Then in the UV, you'll have kappa. So the point with the scalar field is just that the two-point function, this two-point function in the UV doesn't have any, I mean, the natural normalization is 1. So it will probably not give you a lot. So in practice, what you expect is that if you put just a scalar, well, I mean, let me not comment further. It's important that you wouldn't get CT. Yeah. Okay. So yeah, this is essentially what I wanted to say about the Bootstrap problem. Is this one, and then the rest of the talk will be dedicated to deriving this, and describing with some care how do this sum converge, including eventually in the flat space limit. There was some other question, or no? I dreamt of it. Okay. Okay. So there we go to point 3, and immediately to the positive sum rule. Some rules, actually. So, okay, so now we are at this stage. We'd like to study this two-point function. So, well, you could study in generic ADS, so in ADS D+1. And then you will see, and then what would we like to achieve? Well, we would like to achieve something like the following. We want to express some UV quantity as a function of a quantity, as a function of the flow, right? We want to be sensitive to all the B's because it's hard to input in the Bootstrap asymptotic behavior. So some rules are better. And so the way you could imagine to do it is if you can write the limit, maybe I can use some different colors as well. the limit in which the 2 points go together as an integral over the position of the 2 points, right? So this is what we'll do, and this will turn immediately into the sum rule that we need. So the concrete strategy, so the way in which you could address that is to differentiate this equation, and so you write something like d in dx of some function, some ansatz, which up to some kernel should be. So since we also want positivity here, so we would like to get a reflection positive, we need these guys to appear squared for SCBB to work, so we will need a reflection positive configuration. You could do something more general. What we did in this paper, I mean, it would certainly be interesting to close this loophole, but what we did in this paper was to consider the trace. Theta is going to be the trace of the stress tensor. So we try to solve this equation. So find some function c and some function r that solves this equation. And the way you do it is simply, well, you know that you're going to somewhat succeed, or you have a shot at succeeding because there are first-order differential relations involved in the stress tensor because it's conserved. And so you just use conservation, linear combinations of the conservation equations to solve for this equation. And okay, you can write C in a basis of appropriate basis for the 2-point function as linear combinations of these tensor structures, but it's kind of like straightforward technical work. And then you find
Marcos,
how many possibilities there are.
What is C and what is R? I don't understand.
Okay, so these are these are unknowns. C and R are unknowns. And the question is, can we find some function R of x and some function C of x such that this relation is true? If we do find that, then you integrate this relation.
There are always some functions c of x and r x that this relation is true.
Theory-independent functions, right? Of course, if I give you theta theta and I give you theory, there will be some function.
How can it be theory-independent if theta theta is theory-dependent?
Because there exist conservation equations which are theory-independent, right? So there is something that tells you that d mu nu.
I mean, they will be theory-dependent, but in some prescribed way. Is this what you have in mind?
Yeah. So the theory dependence. I mean, so these functions are going to, so this C of x, you write it as, so the theory dependence is, okay, let me be more specific then. The theory dependence is encapsulated in the functions in which you can expand the 2-point function of the stress tensor, right? You have T mu nu, T rho sigma. This will be some sum over effectively 5 tensor structures times some functions, so this, I don't know, T mu nu rho sigma, okay? So the C of x will be some linear combinations, C1 of x, I1 of x, plus dot dot dot. So all the theory dependence will be in I1 to I5, and the C's, the small C's are theory independent. This is what I mean. Yeah, thanks for the question. And this, the point with this is that this I1 to I5 will have a UV behavior, so x going to 0 behavior, which is fixed by the CFT. And so we don't really care much about what C of x is at finite separation. We will integrate this. What we care about is that in the boundary term at the boundary of ADS vanishes, the other boundary term is what we care about. We'll only be sensitive to that. So this is how it works. It's in the same spirit of some logic of C theorem, in fact, except we are in ADS. And okay, I was going to give a direct example because in ADS T+1 we have only one sum rule. And instead of following this strategy, I can just give you the sum rule. Well, I actually, yeah, I will give this and then, okay. So for d greater than 1, we only have the following sum rule, which gives this. And okay, this kernel, I'm not specifying, but okay, it's some simple function of x, rational in fact, if you choose appropriate x. And this gives the expectation value of the stress tensor times the scaling dimension. I will give you just an idea of how to get it directly without having to go through this computation. And but let me first comment that this is not quite the best we could hope for. This is what gives This fulfills the first of the two requirements. It knows about bulk locality by construction. It doesn't fulfill the second of the two requirements because it's not really fixed by the UV, right? The expectation value of theta is really a quantity that depends on the whole theory in ADS. Yeah, delta V is the scaling. Yeah, I'm sorry. Delta V is the scaling dimension. I wrote it here. Let me emphasize it again. Because I erased. Yeah, so we'll always think of a CFT deformed by a relevant operation of dimension delta V. Yeah, so this gives delta V. So let me just say very quickly how you get this and then move on. So the way you get this is by using some conformal Killing vector. So maybe I'll call it U, conformal Killing vector, which is not an isometry. So there is some current associated to it, U nu T mu nu, whose divergence gives theta. So why do we need this? Well, we need this in order for, in the UV limit, this conformal Killing vector will become a symmetry, because in the UV limit we have a CFT. And at the same time, along the flow, theta is not 0, so we're going to get the two-point function. So this we need to pick among the U's, which are not isometries of ADS, otherwise we get trivial zeros. They need to be conformal isometries of ADS. Simplest possible thing is to think about the flat space again with the boundary, right? So since all the isometries of ADS map into conformal transformations that fix the boundary, while you just pick a conformal transformation that doesn't fix the boundary and you have one of these. This is going to be a conformal isometry, which is not an isometry. And okay, so this is the trick, and you can understand, for instance, in Poincaré coordinates, well, in flat space, actually, with a flat boundary, a dilatation centered at 0, I don't know, will move the boundary away. And it's a dilatation, so you understand why the boundary term we pick is going to be delta V. I don't have time to go in more details, but that's essentially what it is. The boundary term becomes a conformal transformation, and so this J mu will become the dilatation currents. It acts picking up delta V, and this gives the sum rule. So this is the only one we have in ADS-T plus 1. And in ADS2, we're more lucky. In ADS2, there's some redundancy in the tensor structures, there's some relations, so you have different solutions to this equation, and you end up getting 3 solutions, which I wrote here just to take a quick look at them, and then we'll focus on the one we care more about. So this has so this is CT, it looks like a G, but it should be CT, so the central charge. You exactly solve this equation in this case using the technique that I sketched because Slava asked, and you get some kernel. This is the kernel R of x that I was saying, and these are the boundary values of the function C of x. So okay, the kernels look a bit mysterious, but that's what you get. What's important is that here we do have a positive sum rule that knows about the bulk and fixes the UV. This second one is just a restriction to the equal to, or the one that I sketched before. And there is a third one that is a bit more mysterious in the sense that it works, but its value on the left-hand side is fixed by perturbation theory in a way which is at least not transparent to us, as in this case. So one would have to go do conformal perturbation theory around the ADS, around the UV fixed point in ADS, and try to fix this value in terms of some physical data, but we didn't get there. We can discuss in more detail why this is not as simple as in flat space, but in any case, essentially because there's dimensionless scale, so it's not as clear that everything is perturbative up to the VEVs. But in any case, this I won't talk about anymore. I just wanted to show the 3 solutions to this problem in ADS2, which are the good sum rule, the bad sum rule because of what I said, and the ugly sum rule because we don't understand it.
Marco, can I ask a question?
Yes.
So this R of x, how much that is fixed by conformal symmetry? It's something you're using it as a measure against a two-point function. So
yeah, so I fix what is fixed by conformal symmetry is the fact that I'm drawing a sketchy coordinate x here. The fact that this depends only on the distance between the 2 points, so the chordal distance. That's all what conformal symmetry gives you. For the rest is these are arbitrary functions. Yeah, and then I'm using the fact that I want a theory-independent R of x as I explained before. So I'm using the tensor structures of the 2-point function of the stress tensor, but this is, yeah. So R of x is arbitrary. Well, it's going to be fixed by this request. Some first-order differential equations that you solve. There's nothing very deep about them. Okay, so good. In particular, the last comment I want to make is that if you take this one and you plug the OP, the boundary OP that I described before in theta theta, you're going to get the function b squared, right? Because I take one theta and the other theta both to the boundary. I commute with the integral and I get this sum rule here. So this is the middle sum rule that we wanted, and we're very happy about it, and we're done. You can also study the convergence of these three sum rules, and these follow essentially from the Tauberian theorem that Jachin and Slava proved. That gives you the asymptotic density of the bt squared for this two-point function, and then you plug it in and you see when it converges. And you see that the good sum rule converges for any relevant perturbations, and this one converges only for very relevant perturbations, which means delta v less than 1. So this only converges for delta v less than 1. Okay, so this one instead will always converge. I would like to move on now to the point 4 of the talk, talking about this remaining sum rule. It's going to be more fun. But if there's question, please stop me again.
Sorry, but is it fair if I say that you're integrating some bulk-to-bulk Witten diagram against R of x? Or is more than that?
Well, we're integrating, I mean, at this level, yes. Once you plug the OPE, you could interpret these blocks to some extent as Witten diagrams, not exactly. The Witten diagrams would be more like Polyakov block for this two-point function, but yeah. Okay, so for off-diagonal sum rule. So how do we get a sum rule from this one? And here I'm just going to set d equal 1 from now on in the rest of the talk for simplicity. So we are in ADS2 all the time. Well, first of all, obviously, this three-point function contains this product, right? Hope this is obvious. If not, you'll stop me. And then, ideally, so the naive thing to do is to just integrate t across, right, with a codimension 1 surface that touches the boundary to get a charge under which the phis are charged. This will ideally give us some rule just because you're measuring the energy of the state that is created by phi. You can map this to global time if you prefer. You measure the energy of the state, you get a sum rule. So this in formulas look like integrating over some surface sigma, the sigma mu with some Killing vector that you can pick. We tried with all of them. And this gives you a charge. This surface sigma is this one, for instance. Well, it should pass through T mu nu, but okay. And but more, this is a drawing that will be more important in what follows. A better coordinate system is obtained by placing the operators at 1 and -1, and then sigma, or the position of the stress tensor, T mu nu, is going to be on a vertical line. So this is sigma. And then the fact that Q with, say, some boundary operator phi gives the derivative, for instance, if you pick whatever, the Killing vector that translates in Poincaré coordinates, you immediately get from this, right, there is an integral, you plug it into, so you plug this integral, you compute Q xi of sigma in phi. This is an integral like those ones, and then you permute with the, you swap with the OP decomposition, and you get a sum. And this sum is simple. I won't write it for time, but it's similar to this one, and it should give delta phi. So let me just call it, I don't know, k tilde. So there's some function of delta, b t delta c phi delta gives delta phi. And this thing you might be happy with at first, and then you will be very unhappy once you try to evaluate it, because you will get that for, say, a scalar field with small delta phi, everything works, but then you increase delta phi, it starts being not absolutely convergent, you increase it even more, and it's just going to diverge. And then you're back to square one. So what did we do wrong? Obviously, this integral is correct, that it gives just a delta phi times phi phi. So what's wrong is swapping, right? Swapping was not allowed. And this is very clear in this picture, so you with a little bit of trained eye, you immediately see that this is a raw coordinate, this coordinate z, Poincare coordinate is a raw coordinate for this configuration. So the OP converges all the way here, it converges above, it does not converge in this point. So here you get killed. At z equal 1, you weren't sure that you could swap. We hoped for the best, and then we got the worst. And then we had to, we sort of got stuck a bit. And then at some point there was a very useful conference at GGI in which Miguel gave a talk. And the solution is called the local block decomposition, which is one of the main gadgets in the paper by Miguel and not Miguel that I was mentioning before. So let me explain a little bit how this is, how this works, and there will be more details in Nat's talk tomorrow. And then I will say how we use this conformal block, this local block composition, and what we actually say something new about it as well. So here it's how it works. So if we look at, we'll have to give one more piece of data, I'm sorry that I didn't give. So let me just say that this 3-point function, for instance, theta of x and then the boundary operators phi phi, is a function of one cross ratio that I'm calling chi. So just to have a name, for the coordinate. And let's look at the space, complex space of chi. So this has some familiar features. It has, if you look at a single conformal block of this decomposition, it has two cuts, one that starts from 0 and one that starts from 1. And this is, as usual, the good cut is the OPE cut. And the Euclidean region is here. So this is between 0 and 1, it's Euclidean. So this is where in this integral, you go from chi from 0 to 1, and then from 1 to 0 in the other sense. There is an involution, so of course it's the same value of the cross ratio. And 1 is the dangerous point. So here there is a cut in every single conformal block, but there is actually no cut in the full correlation function. This is the important point. You can see in various ways. First, well, around 1, nothing is really happening. So of course, it should be analytic here. You can Taylor expand. Otherwise, you can use some locality arguments. So this is one of also the main points in the HKLL construction for a bulk reconstruction. And it leads, so the idea of, one of the ideas of Nat and Miguel is to do dispersion relations, keeping this into account. So if we look at the full correlator, G of chi, they write a dispersion relation with a subtraction with this parameter alpha. So this is a triviality. I'm picking a point around here. I'm using Cauchy theorem, and they put so we put a chi prime here. We divide in order to suppress the behavior at infinity. Why do we do that? Well, we would like in the end. So what if we would like in the end to deform the contour, right? So in the full correlator, using the correct analytic structure, we have a contour like this. We would like to drop the arcs to get a dispersion relation. And okay, this if there is a power law behavior at infinity for this function, if we can prove something like that, and then there will be some alpha large enough for which we can drop the arc. Why is this good? And then we get an expression in which here there is a discontinuity instead. I can start erasing some of this as well, I think. we get a discontinuity instead of the integral, so we get g of chi to the alpha, the integral, and then this integral now is on the cut, minus infinity to 0. And the important point is that there is a discontinuity here. Okay. Yes. Yeah, so chi
Marco,
equals,
can you repeat the question?
yeah, so, sorry, thanks. Yeah, what configuration of points in the original correlator corresponds to special values of chi? So chi equals 0 is the OP limit, is let's say if this is theta or anyway, any bulk operator, it's going to, at chi equals 0, it's going to 0. And therefore, here, the function has power law behavior, and the branch cut here is fixed by the OP. And then chi equal 1, instead you can reach on the Euclidean slice of ADS by just going forward and hitting this point. This is the point chi equal 1. On the Euclidean line, there is on the Euclidean slice, there is no other point except the segment 0 to 1, because in this picture there is an inversion symmetry, which is an isometry of ADS. All the region outside is brought to the region inside, and if you think a little more about conformal transformation, you see that all points here can be brought to this line. And so if you want to go further, well, complex values are going to be obtained by giving imaginary parts to coordinates. And if you want to go further here, you go to Laurentian ADS, and then it will go further. The point here is that on this region, points are space-like separated still, so there should be no discontinuity. Okay. So how this story ends? This story ends by now using the conform. No, it's not an integer in general. We'll find the bound on alpha in a minute, some real number. It will be it might be convenient to choose it related to delta phi, but okay. The story ends by plugging the OP decomposition here, and then commuting these two integrals. And then, so you see what happened. What happened is that now this is integrating only between 0 and minus infinity since we dropped a cut. So the fact that there is a cut in the blocks, this cut here, doesn't matter anymore. I can just compute here, permute, and I get fine functions. And so this gives g of chi in terms of a sum over delta. And then there's our nice product times the new object, which is this integral, but in which instead of a curly g, I put a single conformal block, which are called local blocks. Okay. And now we use this instead of the conformal block decomposition in the integral that we just did there. We again permute the sum with integration, and we get a sum rule with a more complicated kernel that depends on alpha because these guys depend on alpha, which still gives delta phi because that's the same integral as before, and we're fine. And now this should raise questions that I would like to address in the next 15 minutes, and then before concluding. So the questions are at various points. So we did, again, a bunch of dropping and swapping, right? So we dropped the arc here, and then we swapped the integral on the cut for the OP, and then we swapped again here, here, the integral with the sum over local blocks to get the sum rule. How much of this is now rigorous, and why is this sum rule better than the previous one? I would like also to mention that it's important to establish the convergence of the local block decomposition per se, because it's a useful gadget. It will foreseeably be more useful in the future. And in particular, what Nat and Miguel do is to derive from compatibility of this decomposition with the conformal block decomposition some constraints on the form factors, in particular bulk reconstruction kind of constraints. These constraints are subject to estimating what is the behavior of the form factor in this region chi going to infinity. So it's important to understand what this region is. Okay, so the rest of the talk, I will explain a little bit about convergence. If there's time, a little bit about the flat space limit, but otherwise it's fine. I think it's good to drive home that we have good control over this decomposition now. And And so let's go there. Any other questions before? On this for the moment, let me leave it. And this, yeah, okay, I will see what I need. So the main, so convergence. The main point here, so if we look at this, it's not completely trivial how to proceed, because we have obfuscated the Hilbert space interpretation of this thing. Of course, there's still some Hilbert space interpretation, but these are not, the expansion small chi, for instance, does not correspond to primary operators, and this is one of the points. This is not compatible of the OPE for any single local block. So we need some other tool to prove convergence. And the key element is just to use, as one might have expected, Cauchy-Schwarz inequality. So let me just give an idea of what this entails. So the point is that we get a bound for the form factor, so the absolute value of the form factor, an asymptotic bound as chi goes to infinity, which goes as follows. So first, let's understand what this bound, so this wiggle just means that I dropped a constant here. So you could, in principle, track down the constant and get a bound in the sense that the limit of the left-hand side over the right-hand side is less than 1. Instead, this just means that the limit is finite. So this is in the sense in which this is a bound. It's a bound which is a power law bound, so it's already telling us a lot. So it's going to be the key point to decide how big alpha has to be, clearly. It's also not uniform in the argument. So if as I move around in this angle, I lose the bound precisely on the real axis. And so this is actually not quite sufficient on the nose to drop the arc. So we have a power law bound along any lines except one. And then the question is, can we still drop the arcs? Where does this come from? Very quickly, it comes from Cauchy-Schwarz with a mild twist on it. So where you would apply Cauchy-Schwarz, maybe I should change. Right, I should change the pen. More pens are here. The way you should, you would like to apply Cauchy-Schwarz is by drawing the circle that I had before, putting maybe 2 operators here and the bulk operator here, and then you see that this is subject to Cauchy-Schwarz, right? It's a product of the norms, and in the limit in which these points go all close together, you get a bound that you understand because it disconnects. So you get a product of 2-point functions. So this, I'm saying this is less or equal, well, if it's squared, it's less or equal than some product in which I have 4 points times 2 points. These are complicated correlation functions unless I take a disconnecting limit. This is not going to give directly what we want, because here what is lacking is positivity. We don't know whether this limit, which corresponds to a specific point in cross ratio, is going to bound any other point where I put phases, because that point was not positive. So since the b's, I have the coefficients here, these are not positive, so I cannot say that adding phases decreases with respect to Euclidean. The way out is just to consider a slightly different kind of state created by the phis, such that the composition of this overlap is actually just the sum in which the OP coefficients appear in absolute value. And the conformal blocks, small g, I haven't used this symbol before, but let's say the conformal blocks of these correlation functions are replaced by something in which all the coefficients in the small rho expansion are positive. So what is rho? As I was saying, it's essentially this distance, up to square, but it doesn't matter. So I can create a state in which this is actually positive, and then from this one, I can bound this one in the same way, and then I bound my correlator by this. So this explains 2 things. It explains why a bound exists, and it also explains why it's not uniform, because of course when I go to rho, modulus of rho equal 1, I lose the bound, because the right-hand side goes to infinity. And modulus of rho equal 1, as it is common from the 4-point function, understood from the 4-point function, the same kinematics, is this line, chi positive. Okay, so this explains what the main point is. And then from this, everything follows with a little bit of effort. So I will just, maybe I will want to say a tiny bit about the flat space limit. So I will just say how the story goes, and you can ask me if you get interested in it. I can give you more details. There were 3 steps that we needed to prove. One is it legal to drop the arcs? This is still the hardest question. Then the second one is is it legal to swap this sum with the discontinuity and the integral? And the third is, does the decomposition that we get here converge uniformly, so that then we can also swap it with the integral that defines the charge. So first question, dropping the arc is clearly okay everywhere except in this direction, because there we don't have the bound. And you can try to think, okay, it's have a function bounded in all directions except one, it's gotta be fine. And then you go to the math literature and you find tons of beautiful examples of functions that behave very crazily, and they make for wonderful party tricks. You should go to parts and then show these functions, and I mean, I didn't have any success. I don't know why. In any case, the way we resolved the issue was a bit different. We're taking a limit, right, as r going to the radius of this sphere going to infinity. There is only a point here that can contribute, and it can only contribute a constant because we already know the integral here is bounded. This is easy to find. And so since the original integral was bounded and the integral here is also bounded, at most we get a constant out of there. What does it mean in practice? It means that we need to find a representation of a delta function from the integral over this angular direction. Right? So there's a theta dependence, and there's just a delta function that should arise from the limit r to infinity of this integrand here. Intuitively, this will not happen because you have alpha. There will need to be a representation of delta function for every alpha, and every alpha means a different decay in r. So this is the intuitive idea on the basis of which you can throw away this constant. In practice, what we do is to prove that this constant is actually can at most be a polynomial in alpha, and then prove that all the coefficients of this polynomial are 0. But this is the idea. Since we can vary alpha, imagine you find a representation of a delta function for alpha equal alpha 0. You move it a little bit away, it will not be anymore. It will either diverge or go to 0. So that's the idea, and this is how this works. So bottom line, we can drop the arc. The rest is more trivial. You will just use appropriate bounds, essentially still the same bound in terms of these absolute values, to use the dominated convergence theorem here to swap, and then uniform convergence will be also easy to find on some compact subset, which includes this region 0 to 1. So we only proved the uniform convergence, so any compact subset of this kind. So some pi missing a slice, we don't go here because here the integrand is singular, but that's just because that's what we needed. Okay, so the end of the story is that we have achieved 2 things. Once we prove the convergence of the local block decomposition for alpha large enough. Alpha large enough depends on this growth, and so in particular, alpha, this sum rule is true for alpha bigger than delta phi plus delta v over 2. Nobody asked why delta v appeared here. I forgot to say. This is theta. In the UV, theta goes to the deformation, right? It's v. So that's why delta v appears. So this is the bound. Above this alpha, you're good to go. You can use that. And then we proved that this sum rule that we have here is convergent, is actually absolutely convergent, contrary to the other one. Let me also remark as a last point that this same analysis also gives you, via sort of Tauberian considerations, a bound on this sum, through which you can estimate a bound on the convergence of this one. You won't estimate the convergence because there's signs here, so there can be cancellations, but you will say that this is smaller than something that converges with a certain rate. And okay, not very surprisingly, the convergence rate of this is going to be less or equal than if I truncate the sum up to some certain delta m. Well, actually, let me give you the error, right? From some certain delta n. So this is less or equal than something that goes like this delta alpha min minus alpha, where this is alpha min. So it goes to 0, it's power law convergent. All of these extra sum rules, this one and also the one that I erased for the central charge, have power law convergence. For comparison, you apply the same bounds to the original, the naive sum rule that we derived immediately, and you will find that it diverges when delta phi is large enough, compatibly with the examples you can compute, so it all works well. And I will not have time to go into free theory examples, but I still have 5 minutes to talk about the flat space limit. So before that, let me say 2 more things. One thing is that this sum rule can converge also much, much faster. In particular, there's this simple example in which it becomes a finite sum. Why so, or how so? Because here, remember, there was a cut. This comes from a discontinuity, and the discontinuity is such that these guys will contain a sign. Well, okay, it's going to be sine of pi times delta minus 2 alpha, yeah. So this should be sort of familiar from all the functional bootstrap, etc. And it's indeed another point which I think Nat will emphasize more in his talk. So if we have a free theory, for instance, we can pick this so that all these signs are 0. And this reduces to a finite sum. You should ask why there is a sum at all, but I won't tell you that unless you ask it really. But in any case, it's a finite sum. Infinitely many of these are going to be 0. So these are all bounds on the rate of convergence. They're by no means optimal. On the other hand, there are examples in free theory if you pick differently this alpha, for which you can maximize the number of terms that contribute and saturate these bounds. Correspondingly, free theory, a free boson manages to saturate the power law in this bound as well. So it's all consistent. And this is what I wanted to say. Let me just then say a few words about the flat space limit. I still have 5 minutes, if I understand well the clarifying emails that Slava sent yesterday, and then I'll conclude. So, yeah, I will erase again. Are there more questions about this construction? Yes. Yeah.
Can you just explain a little bit? Was it important that the point approaches from below and the other ones from outside, or?
No, you can find bounds. It's just a bit easier to visualize because it's an overlap, and then you use really Cauchy-Schwarz.
I was just a bit confused. I thought you create a state that evolves from outside, and then it hits that, and then there is another one from inside. So I did not understand the picture when it comes from.
Okay, so
shouldn't theta come from outside? Is my question for this picture to hold.
Okay,
or it doesn't matter.
Yeah, let me try to explain this, and then you tell me if it's still not clear. So here I'm doing radial quantization around a point, say this point. So I do radial quantization, and I look at states on the unit circle. Since I put theta below the unit circle, on the unit circle I have a state created by this theta.
Sorry.
And
it's
outside,
it's clear. So
okay.
it needs to be like this. Sorry.
Yeah.
What I was saying was wrong, of course. Okay, thanks.
You don't. This phi tilde are related to phi. I just look at the state created by phi, what the decomposition is in terms of primaries. This will have some signs which depend on these coefficients and on the conformal blocks. And I will just modify term by term this phi tilde by some phases that cancel these signs. I do not know what these phases are, but I know there are phases. So this modification does two things. It gives me products with absolute values, and it doesn't alter the norm of phi tilde because I only multiply by phases in an orthonormal basis. So it gives the right-hand side is unchanged, but the left-hand side now has absolute values, so it bounds everything else.
But I'm confused with this operation because before then you knew that the state phi was normalizable because its norm was a 4-point function, and we assumed that the 4-point function is finite.
Yeah.
And so the norm of phi tilde is what? It's something.
It's what I said. It's not changed because I take phi.
Yeah.
I just expand in an orthonormal basis in which I have some O delta. They're all orthonormal, and these are some coefficients A delta, and I multiply by phases some phi that depends on delta, and of course the norm is unchanged. Yeah.
Okay.
Thanks.
Okay, thanks.
Okay. More questions? Otherwise, I'll erase.
Is it like the first time that you managed to justify that some arcs which people drop can actually be dropped, or are there?
I mean, this question can be taken in two ways. It's the first time that I managed to do that, it's true, and it's also it's kind of the first time I tried.
No, but I'm happy that you did such a careful job. But
Yeah, I don't know if I didn't look around, so I'm sorry. If somebody else did this before, I mean, it didn't look so. Yeah, to my knowledge, yes, it's not, but it's not rocket science. I don't know. It's okay. It's a careful job, but you can do the careful job.
well, it was.
Yeah, so it's good. It's good that it can be done. Yeah, it's good that it can be done. Okay, so flat space limit. Well, I will really just say 2 words because I want to conclude on time. So eventually, as we were saying, we would like to get to flat space. So since there's also papers already done in flat space, it's good to have formulas that connect these things, and to see where these sum rules, what these sum rules become in the flat space limit. And so for this, we guessed or derived in a not completely rigorous way. I will make a comment about this in a second, but formulas for how all these items in the list, what do they become when you take the flat space limit r going to infinity, which maybe I did not emphasize enough. It's the limit, this is the limit that is written on this board, this lim here, in all these formulas that I'm explaining in a moment. It's a limit where delta phi goes to infinity, all the scaling dimensions in the spectrum also go to infinity, and you're isolating some ratios by putting delta functions. So this is the flat space limit because I think I drew this, I wrote this formula at some point, but delta goes like some energy in flat space times the radius of ADS. You can just derive this formula in one line by looking at the metric of ADS and taking the flat space limit. Okay, so the S matrix formula, this one appeared many times in the literature. There are tons of people in the audience and not in the audience who have worked on that. I will not cite them, but please feel like if you have been cited. Essentially, what's important is that there is a kernel which is known. There's a sum of blocks, and there's a phase. So where does this phase come from? Comes from the fact that you need pi global time to have a scattering event. So you need to evolve for pi. And then you need to evolve for a time equal to pi. So this is pi times delta. And then there's normalization, this kernel, this subtraction here, which essentially make this into the interacting Hamiltonian. Essentially, the role is to say, I want S equal 1 if I just plug free theory in. And this more or less fixes the formula. There is this 2 to the delta phi. The 2 is also part of the normalization. It gets you to free theory. And this delta phi you can sort of combine with the sum. And if you look at, for instance, a spectrum of scaling dimensions a little bit away from free theory, 2 delta phi plus 2n plus some gamma of n, you will see that this times this will turn into an integral, in d delta divided by delta phi. It's just the bin size as a 2, and then if I divide it by delta phi, it's a 2 over delta phi. So this integral times the delta function will give smooth functions of S. This is essentially what enters in this formula. And then this is sort of a way to understand it, and then it has been derived by more and more degrees of accuracy in the last few years. So okay,
one of the important points is that this delta function can be made sense of, right? In a discrete sense.
Yes. Yeah.
The delta function is really some Gaussian with a width.
Right. This goes into what I was saying is like you can have more and more degree of accuracy and rigor here. So Miguel, Lucia and Ifei have a paper in which they make this very precise, and this is best understood as a delta as at finite radius is best understood as a Gaussian, in which has some width which is much smaller than delta phi. In particular, it goes like square root of delta phi, and there's a normalization such that in the limit delta phi going to infinity, it will become this delta function. But it's true that this formula will make sense also before the limit if you smooth it out. Very good. And then you can add 2 other items to the list. One connects the two-point function of the stress tensor, of the trace of the stress tensor, to the spectral density in flat space. So, well, I'm actually almost over time. So let me give you just an idea. So the two-point function of the stress tensor in flat space, you can do a Schelling-Lehmann decomposition, you get some spectral density. So there should be a relation between the two. And okay, it will need to have the OP coefficient squared. And then again, some kernel. How do you fix the kernel? Well, you use the sum rule. You know that the homologic of C theorem in flat space gives the central charge as an integral over the two-point function. And this you can just compare with the flat space limit of the sum rule to fix this H2 of delta, and then everything is fixed. And then for the form factor, it's similar. There are the sum rule, well, okay, you know you're going to have the product of the two OP coefficients. The rest of the structure is more or less the same. Notable feature only pi half, because in this case it's a form factor, so I erase half of the diagram and I put an operator here. So I only evolve by pi half. And then the rest of the normalization are fixed by flat space relations and the sum rule. The sum rule in flat space is just that F2, the two particle form factor of theta at the origin momentum space is minus 2m squared. This comes from, again, from momentum conservation. It's just p mu. At zero momentum, you just have the integral of the stress tensor. And this m squared is related by the formula above to delta phi. And we had the sum rule that I erased that gives delta phi. So you use that sum rule to fix this kernel into the product of the two. Or essentially, you can just fix the whole kernel by the sum rule. So this contains some degree of heuristics, and because I'm sort of telling you how this formula looks like, but you can be much more careful. And then, in a very acausal way, this particular formula that we derived in this sort of non-rigorous way was derived rigorously 1 week before when Miguel published the paper. So for a rigorous derivation of this formula, essentially you do the same as for the rigorous derivation of this. You pick operators with the correct imaginary parts in their insertions times in their coordinates, and you take the flat space limit and you get exactly this formula. It's time to conclude. So what did we do? What did we learn? And what's in the future? So we described a method to inject bulk data in the bootstrap of quantum field theory in ADS. And this specifically led us to convergent sum rules all the way to flat space, which in 2D know about the ultraviolet. In particular, they isolate the ultraviolet in the sense that they depend only on the central charge, this sum rule here. And in higher dimension, they know about the bulk, but they don't isolate the ultraviolet alone. Along the way, we proved the convergence properties of the local bulk decomposition, which is useful per se in the bulk reconstruction program. Again, shout out to the talk by Nat tomorrow. It's a bootstrap system. We can apply it numerically, apply it in the numerical bootstrap. What are natural targets? Well, there's targets that have been touched before in the papers I mentioned along the way, in particular Sine-Gordon, for instance, which is integrable. ON model is also integrable in flat space, so we know what we want to get. We can see how close we get. Another natural possibility is, to start with, is the Ising field theory, which was also mentioned at various points, like it's a subject of this week's lectures. And for this, we can compare with the flat space analysis, most directly the paper by Miguel Correia, Joao, and Antoine, and the previous work by Barak Gabay and Shi on the theory. So we know quite a bit about this theory, even if it's not integrable, and it would be nice to see what this system gives us from ADS. Thank you.
I have a very technical question. So that point where you remove the phase and put absolute values, it reminds a little bit when you have this matrix bootstrap, there are these screening regions where you can get cancellations, and we never know how to get rid of this screening. Is this an operation that has a flat space analog related to this screening, where T and S channel densities could cancel each other, or it has nothing to do?
I have no idea. So the first part of the question, does it have a flat space analog? Could we do it in flat space? So this would mean something like in this formula, for instance, replace with absolute value here. How do you do that? From two particle incoming states, which are plane waves, without altering the norm, right? That's what you want to do. The problem there seems to be, okay, so naively you would need a function of the momentum, right, of S, because your natural complete set of states is now continuous. And then you need to, the fact that this function should exist looks reasonable. These phases will also probably vary slowly. But the normalization of the flat space states is not finite, so
But why would they vary slowly? Because the point is precisely
No,
that because we cannot bound them, that they can vary super crazily.
No, exactly. So the
and
second
cancel
sentence,
each other.
yeah, the second part of the sentence was meant to erase the first, in the sense that it would vary slowly if the state was normalizable, but since it isn't, then I don't know. Yeah, maybe it's just crazy, and yeah, I haven't thought about this, but this would be more or less the way in which it would go.
In cases where that sum rule basically collapses to a single tower, like in integral cases, I think what you're describing is you write the form factor basically as square root of S times something, and then you just put an absolute value on that something. But it's only in this very special case. Otherwise, you know, these things are fluctuating on scales much smaller than large delta, right? So you're doing something very weird. So I'm not sure if it has a nice flat space interpretation in general.
Thanks for the nice talk. So, so you get this sum rule by putting the local block decomposition into the ward identity for the stress tensor. So do you think that this, like, will this sort of completely capture the locality, or?
That's a very good question. I don't know. So I suspect not. The naive reason to suspect not is that your functionals have two indices, right? They have alpha and n. And here we're getting rid of n. N is a proxy for chi, for the cross ratio, and you turn the cross ratio into n, and we get rid of the cross ratio by integrating. On the other hand, your functionals do have relations which involve n and alpha, right? So you can get rid of some of them by shifting alpha. But you can also, it looks like, since there is this bounds on alpha, you cannot get rid of all of them. So probably there's still more in your function. It would also be interesting to maybe add them up in this story. Like this is a bit causal again, but the kind of constraints that Nat and Miguel get are constraints of the kind that some functional applied to a crossing equation gives 0. And we wanted something in which we could see like a left-hand side, well, in this case, like, okay, delta phi, some left-hand side that you could put in the bootstrap, and so we integrated. So otherwise, you could take your function, for instance, isolate one term that you know or you want to bound and use those. So there is a question whether this captures more. And the answer naively could be yes, because there's more functions in just the local block decomposition and the Polyakov bootstrap that you guys do, but it's not clear to what extent because of these relations between alpha and n. So it would be interesting to work it out, yeah.
Yeah, because naively you might say the fact that this local block decomposition equals the regular block decomposition, so the equivalence of these two sums, this is basically locality. So you're kind of using this by swapping to the local block sum.
Certainly we are using, but the point is how much of it is needed, right?
Then you integrate.
We're integrating, right?
So you lose constraints.
Yeah, we lose the n, but n is not independent, right? You have some relation between n and alpha. So I think the answer is no, we don't use the whole locality constraint, but I don't know how many more. Yeah, this is something that I actually wanted to ask you guys about the paper. We can discuss later. Yeah.
More questions? If not, let's thank Marco, and I have an announcement to make after.
Thank you.
Okay, so first